too many of us to be having the discussions. I think it'll get too clouded. So if what you can do, if you have something to say, put it in the chat or click the put your hand up button, and I'll try to answer them as they sort of come up. It'll be a little bit of back and forth. So if everyone can just be patient, it's probably going to go a little slower than a normal presentation, but we'll try and muddle our way through it. So, oh, it's Dan's birthday. Happy birthday, Dan. Are we allowed to know how old Dan is? Old. Oh. All right. So, as with my class yesterday, no going to the bar until the sun's over the yard arm. Okay. So that means noon, everyone. Noon. Oh, yeah. Thanks for that reminder, Adrienne. That's kind of a little bit sad. Well, I'll have to raise a virtual toast to Daniel. Okay, it seems like a few people are sort of flipping in and out of connection. I'm not sure if that's because they're home internet. But I think at this point, we'll get started here. So I went back and just looked at the schedule and saw where we were, and we're just over a week behind in where we should be right now. We are as up to date as we can be with the quizzes. So the next quiz we're going to have is on the material that we'll be talking about today. So stand by for that. And so today what I'm going to be doing is we're going to do an hour of lecture. Everybody's going to have a little break for a bit, and then we're going to do another hour of lecture, basically. And this is an attempt to try and speed us up. And then this afternoon, I am going to be giving a demonstration of the pump curve. So today we would have been in lab and collecting pump curve data for the next lab. So what I would appreciate it if everybody could do before this afternoon's demonstration is if you can read through the lab, the pump lab, and so you have sort of a general idea of what I'm going to be talking about. Now, since we're not going to be actually doing this lab, I'm just going to be doing a demonstration of what a pump curve is and what it means. There is going to be no lab write-up, okay? So has everybody got that? So the lab that you just handed in to me, the system curves lab, will be your last lab for wet 122. So that's how I'm modifying our outcomes. Does anybody have any questions about this? Yes, the popular point question is still due. Yes, please email it. Yes, it's due today. Any other questions about sort of the schedule? Okay. All right. Well, on that note, then we are going to get into our lecture for today. So I'm going to, I guess maybe before I do that, does anybody have any other questions regarding this shutdown of regular classes? Any concerns about anything? Okay, hearing none. I am going to go into our presentation. All right, so right now up on the screen, you should be able to see our PowerPoint slides, just like I would do in class. So I'm going to just flip on to where we had left off last week. We had talked about different types of pumps and how distribution systems are configured, including the high lift pumping station, the booster stations, reservoirs, and this was further built on by what we saw on our field trip last day. We talked about recirculation and transfer pumps. We talked about well pumps, another example of a well pump, and then other sort of feed pumps. And then this is where we started getting into talking about centrifugal style pumps. So the centrifugal pump is the workhorse of a water distribution and wastewater collection system. They're used in booster stations for distribution systems. They're used in lift stations and wastewater treatment. And then the other type of pump that we see, which is a style of centrifugal pump, but it has more what they refer to as stages. So it can add more energy head into the water because it needs to lift the water usually to some high elevation, is a vertical turbine pump. Now, vertical turbine pumps, unlike sort of a standard centrifugal pump, can only be used for clean drinking water style applications. So there's lots of different reasons why centrifugal pumps are used, but the main reasons are that it's a relatively simple technology. If you look at the guts of it, it's a spinning impeller, and basically as that impeller spins, it adds energy to the water, and that energy can be in terms of either pressure or velocity or both. So it's not particularly high tech. The centrifugal pumps, they can be quite compact for the amount of work that they do, so they can fit in small spaces, which is really important when you're moving them in and out of pumping rooms or pumping houses and things like that. They're relatively low cost, and that ties into the fact that really we have a shaft that rotates with an impeller on the end of it, and that's really as high tech as it gets. I mean, there are accoutrements you add on to that, and if you get, well, maybe not this year, but next year, Owen to show you a jet pump, he can show you some of the other things that are included in that. Now, all centrifugal pumps belong to a larger category of kinetic pumps. And they're called kinetic pumps because they basically give the water velocity energy, and then that velocity head is transformed into pressure head. So kinetic meaning moving. So what we're going to do here is we are going to watch a little video about how centrifugal pumps work. And I'm really hoping that you'll be able to see it. So just stand by while I get there. Okay. And I'm going to share. So just wait a minute while this should pop up on the screen. Hi, there it is. Okay. Maybe. Do. All right.
Centrifugal pumps are the most preferred pumping devices in the hydraulic world. In this video, we will have a conceptual overview of working of centrifugal pumps. At the heart of the system lies the impeller. It has got a series of curved vanes fitted inside shroud plates. The impeller is always immersed in water. When the impeller is made to rotate, it makes the fluid surrounding it also rotate. This imparts centrifugal force to water particles, and the water moves radially out. Since rotational mechanical energy is transferred to the fluid, at discharge sides of impeller, both pressure and kinetic energy of water will rise. At suction side, water is getting displaced, so a negative pressure will be induced at I. Such low pressure helps in sucking fresh water stream into the system again, and this process continues. This is the reason why priming is important for centrifugal pumps. If no water is present initially, the negative pressure developed by rotating air at eye of impeller will be negligibly small to suck fresh stream of water. Impeller is fitted inside a casing, so the water moving out will be collected inside it and will move in the same direction of rotation of impeller to the discharge nozzle. Here you can note one specialty of casing. It has got increasing area along the flow direction. Such increasing area will help in accommodating newly added water stream and will also help in reducing exit flow velocity. Reduction in flow velocity will result in increase in static pressure, which is required to overcome resistance of pumping system. Here you can see more details of vanes inside impeller. They are backward curved vanes with state-of-the-art eye configuration. This vane is extracted from a Kirloskar pump model. If pressure at suction side of impeller goes below vapor pressure of water, a dangerous phenomenon could happen. Water will start to boil, forming vapor bubbles and spoil impeller materials over time. This phenomenon is known as cavitation. More the suction head, lesser should be the pressure at suction side to lift water. This fact puts a limit to maximum suction head a pump can have. Careful pump selection is required to avoid problem of cavitation. Current impeller type is enclosed. Semi-open and open impellers are also in use depending upon application. If the working fluid is cloggy in nature, it is preferred to use open kind of impeller, but they are slightly less efficient. Mechanical design of centrifugal pump is always challenging. A shaft is used to connect between the impeller and motor. Since water pressure inside casing is huge, a proper sealing arrangement is imperative in arresting water leakage through shaft casing clearance. Mechanical seal or stuffing box-based mechanism is used for this purpose. Impeller is mounted on bearings, but at suction side of impeller, it is not advisable to fit a bearing since it will block the flow. So bearings have to be fitted at the other end. This means impeller is mounted like a cantilever. For high flow rate pumps, a bearing housing with cooling oil is necessary for improving life of bearings. We thank Kirloskar Brothers for their technical support and creation of this video.
Okay, students, I'm going to try and stop this. All right. Okay, can I have a show of hands? Did you guys manage to see that video? Okay. All right. What I'm going to do now is I'm going to back up and I'm going to answer some questions. I'm glad that you saw them. So Richard today says, is cloggy the official engineering term for cloggy fluids? You could use the word cloggy. We could use high suspended sediments. That could be another term you could use. Viscous. But really, when you're talking about impellers, the open style impeller is something that you would use to move sewage, and the closed impeller that's got these shrouds around it, that's something you're going to use to move clean drinking water. So that's the difference between them. Does that answer your question, Richard? Okay, great. Perfect. So what I'm going to do is I'm going to go back into the PowerPoint again here. Hang on one second, folks. Okay, share files. Share now. Okay, sorry, I was having a little hard time loading here, so please stand by. Okay. Dan, did you have a question? How about Kelsey? Did you No, all good. Happy 22nd, Dan. That's good. Okay. So the idea with this, when we're looking at what the inside of a centrifugal pump looks like, the water goes in here, okay? Right in this area. So this is called the eye of the impeller, okay? So if you can imagine that if you had a pipe coming directly out of the screen, that pipe would be feeding water into the eye of the impeller. Then what happens is the impeller spins and that water gets flung out to the edges, okay? And it just basically starts spinning along with the impeller. So the water sort of spins in the direction that the impeller is moving. Now you'll notice, as they said in the little video, the cross-sectional area of flow up in this area here, which is called the cutwater, is very, very small, as opposed to the cross-sectional area of flow up here, where the water is getting ready to discharge, is quite large. Now this is a twofold process. The first reason why is when the water gets initially spun out of the eye and the impeller, we want all the energy to be in the form of velocity head. So that means we need to have a low cross-sectional area because we need to have our velocity quite high because we want the water to be moving in a very high speed up in this area. Then as the water spins around in here, the cross-sectional area gradually increases. So that velocity head then gets transformed into pressure head because we know the relationship between velocity head and pressure. As the velocity goes down, because the cross-sectional area has gone up, that energy has to be converted into something. So it's converted into pressure. So by the time the water leaves out the discharge side of the pump, it is relatively low velocity water, let's say 1 meter per second, but it is very, very high pressure, okay? So the cut water here causes that increase in velocity in this zone, but it also forces the water to leave the discharge side of the pump. Does anybody have any questions about that? Okay. So what I'm going to do is, oh yeah, that's a good question, Stuart. No, what happens, and this is something I will get into a little bit later. So Stuart just asked if the water can't leave the pump, what happens? So in that case, the water is forced back into the cutwater and has a rapid increase in velocity, super, super high velocity. And so when that happens, we have something called discharge cavitation that happens when we have that super high velocity transfer of energy. So it goes from pressure to velocity at that point. We see a very rapid drop in the pressure head. And we see pressure so low at that point, we can actually cause the water to boil, because there's two ways we can make water boil. We can add heat, or we can reduce the pressure. And in this case, we reduce the pressure so that we have water starting to boil. And we'll talk more about that in a little bit, but you won't break the pump immediately, Stuart, but you cause extreme problems with overheating as the water spins inside the volute. You will cause vibration. You will cause cavitation damage to your impeller. So it's really, really not good. All right, so this video, or this little picture that I've given you here, this is just another sort of diagram showing how the water comes into the eye of the impeller. It enters inside the impeller, so you can see this is a closed impeller, so it's got two shroud plates along the edge, so the water goes inside those shroud plates and pops out, and then is spun in the impeller and discharged. Okay. Does anybody have any questions? Okay, I'm just going to go on to the next slide here. And again, this is just another view. I've tried to give you a few schematics that you might find helpful. So, I'm not expecting you to be pump experts, but you should be able to name the primary parts of a centrifugal pump. So, hint, like exam question, okay? So, be able to do that, please. All right, so this again should provide even more clarity, Richard, for your earlier question. So these are two types of impellers that you see here. So the top is a closed impeller, so it's got the shroud plate on the top and the bottom. And actually and you can't see the vanes. The vanes are actually inside, in between the different shroud plates. Now, this second type of impeller that you see right here, this is actually a semi-open type impeller. And it's called the semi-open because you see at the bottom of it, it's got a shroud plate located on one side of it. Okay. So a full open impeller has no shroud plates on either side of it. So you would see a open impeller in a centrifugal pump that was used in a sewage lift station, because you are going to be pumping things that you get solids in there, obviously the things that you expect in sewage, but you also get a lot of weird things like rags. I just saw a little video or a little picture from one of my online forums I follow where there was a whole pair of men's underwear stuck in the impeller. So I saw another one where a rat had gotten into the impeller. I don't know how that happened, but anyhow. So what we're going to do now is we're going to watch a little video on the different styles of impellers. And that's where I'm going to go to next here. All right, so you can see that. That's great. And I'm just going to play it here. Maybe. Stand by a second, please. Seems like there's a bit of a lag when I bring up these videos. So if everybody can just stand by for a minute, please. Maybe. One of the things that I heard was happening yesterday with Collaborate was that it seemed to struggle with some of the applications. So students, I think what I'm going to do, instead of spending more time trying to get these animations to work, what I'm going to do is I'm going to email you the links, and and then you can watch them on your own. And then if you have any questions regarding it, you can flip me an email and we can discuss them. Okay, now my computer is completely frozen. Whew. All right. So I apologize, folks. I can't seem to get that running in this. Kelsey, your hand just popped up. Do you have a question for me? Okay. All right, so we're going to get back into, so I will email you that animation, and I'm going to email you the next animation since the computer seems to really be struggling to get those up and running. All right. So I'm going to leave that animation behind. And now we're going to start talking about energy head. So the whole purpose of us adding a pump into a system is to add energy. So far, we've really been talking a lot about the energy that's added from moving water to a reservoir and having the reservoir being the driving energy source, usually in the form of elevation head. And we've talked about head losses. So now we're going to talk about head added. And so pumps add head. Now, when we talk about a pump, it has basically two types of head that we talk about. And the first is the total static head. So even when a pump isn't physically moving water, it has to provide enough head in order to match the static head conditions in the system. So if you are using a pump to pump water to a reservoir that's located 100 meters above a hill, up on a hill, your pump has to be able to provide static head that's 100 meters, because we need our hydraulic grade line to be flat, because when water's not moving, it means we have a flat hydraulic grade line. So under no moving conditions, that pump needs to put in 100 meters of energy. Now, once the water starts moving, we have to add more head, because now we're going to start having head losses. We're also going to have some requirements for some velocity head, not very much, but a little bit. So we're going to need to add more head over and above the static head requirements. And that's called our total dynamic head. Now, if we look at our Bernoulli's equation, which so far we have been referring to it as our energy at point 1 minus our head losses is equal to our energy at point 2. But now we have an additional parameter, which is our head added. So our energy that we have at point 1 plus any head that we add with our pump minus any head losses is going to equal the finishing head at the end point of our hydraulic system. So our energy equation just got a little bit more complicated. Hi, Jared. So now we're going to talk about these two concepts again using some diagrams. So here's an example where we're just looking at static head. We've got no flow happening. So I've got two pumps each pump is pumping from the same reservoir. So I've got a pump here, and it would be extracting water, and that water would be flowing up into this particular reservoir. Okay. This pump here would be extracting water into the eye of the impeller here, and then it would be discharging up into this reservoir here. But right now we have no flow. So Q equals 0 in this pipe and Q equals 0 in this pipe. Okay. So in this case, the pump still needs to provide enough energy to make sure that the water doesn't come back down the pipe, because we need a flat hydraulic grade line. So this energy that we have at point 1 in the system has to be the same as the energy that we have at point 2 in the system. Or in this case, if we're going in this direction, this would be the energy at point 2. Okay, so when we say that, we need to provide the total static head. And in general, we kind of don't care where the pump is located. What we care about is where our water levels are. So we need to know that this pump, regardless of how it's configured, needs to provide enough energy such that it overcomes this head differential. Okay, and that's from water level to water level, or water level to water level with system pressure, because sometimes we're not pumping directly into a reservoir, we're pumping, let's say, into a pipe, and we've got pressure. So we might need to make sure that we meet the elevation requirements of this point, but also the pressure head requirements. And this is still under no water moving conditions. All right. Now, this goes back to the original thing. You say here, we've got a pump sitting here, we've got a pump sitting here. Kind of where those pumps are sitting relative to the water levels don't matter. What matters is that each one of them is going to be able to provide this overall static head requirements. Now, the pump here is giving all the energy in terms of discharge head, and the pump here on this side has basically dividing up how it's delivering energy to the system. Basically, on this side of the pump, it's giving energy to the system in terms of suction lift, and on this side, it's giving it in terms of discharge head, whereas over here, it's all discharge head. But regardless of where your pump is situated, it still needs to provide this much overall level of head in your system. Is there any questions out there, folks? All right, so I will carry on. So what we're going to do here is we are going to figure out what is the flow rate under the static head operating conditions for this little system. We're also going to figure out what the head losses under this for this system are. We're going to calculate the static head that the pump has to meet at point A of this system. So I'm going to put this first question out to the group. What is the flow rate under static head operating conditions? Awesome. I'm getting a lot of Q is equal to 0. Aaron said 1. All right. So that is absolutely correct. So the minute you see static, you know that we have no flow. Okay. Now the next thing is, what are the head losses under those conditions? Again, taking that out to the team, what are the head losses? Awesome. Okay, great. So the team has saying that the head losses are 0 also, and that is absolutely correct. Again, just a reminder, your head losses are completely dependent on your velocity. If you have no velocity, you have no head losses. And in this case, we have no flow rate, so we have no velocity. So we've answered our first question. So the next question that we're going to answer is, we're going to calculate the static head that the pump has to meet in order to meet the system requirements shown at point A. Now, I realize it's covered up a little bit here, but this down here, that says 50 meters. Okay, so when we take a look at this, our pump needs to provide enough energy so that it can take the water from the static water level here, and I'm going to call that 0.1, and give it all the way over here, and I'm going to call that 0.2. Okay, so it needs to add all of this energy so that we have basically a flat hydraulic grade line because we have no water movement. Yes, point A is point 2. I'm just calling them 1 and 2 for the purpose of the analysis. But I want to know what the static head that the pump has to produce. So I'm actually saying, okay, how much energy does my pump have to put into this system in order to create a flat hydraulic grade line? So the first step of this is to calculate the total static head at this point in the system. Okay. So we want to know what is the total energy at this point. So we have energy in the form of elevation, which is equal to 52 meters of head. And we also have some pressure head. Oh yes, can everybody see my writing on the screen? I should have asked that. Okay. Okay, good. Great. So I've heard, Josh, that Chrome works the best, but I don't know if that's true or not. So the next thing we need to do is we need to figure out what the pressure head of our system is, because our total energy head at 0.2 is going to be equal to our pressure head plus our elevation head. So can anybody tell me what my pressure head is at this point? Break out your calculators, folks. I may not be able to physically watch you do it, but I'm mentally staring at you all. Yes, that's right. So basically, our pressure head is a function of our pressure, which is 450 kPa divided by 9.8. And we end up with it at approximately 46 meters of head. So I'm just going to sort of correct this again. So at this point, just to neaten it up, we have 46 meters of pressure head. We have 52 meters of elevation head for a total amount of energy head of 96 meters. Oh, 98 meters? I can add. Is that right, everybody? Okay, great. I'm glad I can do math on the screen. All right. So what that means then is our pump, in terms of both suction lift and discharge head, has to provide a total of 98 meters of head in order for us to meet the static requirements of the system. How does everybody feel about that? Okay. I'm not hearing any remote. Oh, okay. So a comment from Megan was, I'm kind of uncertain why we have to add them. Remember, Megan, that regardless of the form of energy it is, so at this point, at point A, we have both elevation and pressure. So we have two types of energy at that location. So we convert them. One's already in terms of elevation, but our pressure is in terms of kPa. So we convert that into meters so that then we can add basically apples and apples to get a full representation of the total energy that we have or that we are requiring at this point in the system. All right. Did that help you? Okay, good. All right, so we're gonna continue on here. Now, this is a pretty complicated looking diagram that we've got going on here. So this is our total dynamic head requirements. So you're going to see elements of the things that we saw in our static head. So if we take a look here from here, this point here to here, that's called basically your suction lift. Okay. So your pump has to provide energy in order to get the water from here into the eye of the impeller. Okay, so that's its first job. And it's also going to encounter some head losses in this pipe. It's going to have to add some energy, so it has some velocity energy. So that's what we're looking at down here. We've got our friction losses, which are right here. We've got our velocity head requirements, which basically we've made the water move. And then we've also got our just static requirements of getting the water from this point to this point. So a change in elevation. Then when we look on the discharge side of the pump, we have to move the water from the center of the pump up to the top of the tank. So that's our original static head. Okay, static discharge head. But again, when we look up here at the top, we also are required to give this water some velocity. We're moving it along. We've got to get some flow rate. So there's our velocity head. And you'll notice it's just little because our velocities are always really low in our systems. But we also have friction. So we have head losses that happen inside this pipe that we have to account for. So our total dynamic head is a function of both the static head, of just the difference between the elevations of the water, plus the amount of energy that's required to give the water some velocity, plus the amount of energy that we have to pay in terms of head losses or friction to move the water through the pipe. Now, there's also another type of head that we need to add into the system, which is called the net positive suction head. Now, this is a bit of an operational consideration, but what I will tell you is that the net positive suction head, it's helpful for students to think about it in terms of as the water goes through the pump itself, it has friction. So there's lots of turbulence and things that happens in there. So the pump actually needs to be able to provide energy to overcome its own friction losses. And that really is the net positive suction head. And that varies from pump to pump. Some pumps have more net positive suction head requirements than other pumps. And we'll talk a bit more of this. And that also is a topic that we're going to get into doing actual calculations with in WET 222. All right, so hi, Erin. It's not so much that the pump wouldn't spin. The pump would still spin, But what would happen is the pump would experience something called suction cavitation. And this is different from the type of cavitation that Stu was asking me about earlier, which is discharge cavitation. You have suction cavitation, you have negative pressures developing at the eye of the impeller. Well, pumps are always very, very turbulent, Aaron. Always. We know this. It creates an incredible amount of turbulence. If you think about the idea of water coming into the eye of the impeller, doing a 90 degrees, getting flung out to the edge of the volute through the impeller, getting spun and changed direction through the volute. So it is a very, very turbulent process. And so the net positive suction head sort of takes into account all of that. All right, so here we go. We've got an example here that is quite complicated. And I know I said I would lecture from 9 to 9:50, so we've only got 3 minutes left here. So what we're going to do is we're going to stop before we get into this example. So I will ask everybody right now if you could just give me a thumbs up or that you're doing okay and that you can still hear me. Okay. Awesome. Okay. Yay. Okay, really good, people. All right. Okay, so what we're going to do now is, I know this sort of lecturing online is super, super weird. I'd like everybody to go stretch their legs, have a bathroom break, maybe get another cup of coffee, and then we're going to reconvene here at 10:15, and I will lecture for another 50 minutes. And so we're going to start with this problem when we get back. So make sure that you have paper and your calculator handy, because this is going to be the culmination of it's going to use all our skills from the last section. So we're going to be doing major losses and minor losses calculations. Oh, hi, Aaron. No, there are, Owen isn't, sorry, excuse me. Owen isn't running labs today. Okay. So make sure that you have access to all of the charts and tables that you had for section number 4, because you'll need them to do the minor loss calculation. So